Hello everybody, I am Merve Yuzgeccioglu. I am a PhD student at Teknische Universiteit Dresden and early stage researcher of 5G Virus project, which is funded by European Commission. In this video, I am going to talk about performance of media-based modulation in multi-user networks. Throughout my talk, I will first explain you what media-based modulation is, and then give you the system model from single link to multiple access channel. Later on, I will show you the achievable rate expression of these two system models. Then we will look into the performance of the system and I will conclude my talk. So what media-based modulation is? Imagine that this is a transmit antenna and we place passive RF elements around the transmit antenna. And when we changing the on-off status of these passive RF elements, we can let the wave go through or not, and every combination of these RF elements will actually change the appearance of the channel at the receiver side. So this might be the result of one combination, and this one might be another generalization resulting from another combination. So we have total MP RF elements, and as a result we have m different combinations that we can realizations that we can generate by using these NP elements. X is the vector that contains all the channel realizations, and xm is the mth entry of this vector. So there is a message coming to the transmitter, and we map this message to one of the channel realizations by changing the by choosing one of the combinations of the RF elements, and then we send the signal through the channel. In this work, I have assumed that channel is uncorrelated fading and receiver has perfect CSI. So if we look into the single user link case, we have XM, one of the channel realizations, and P is the total transmit power, N is the additive white Gaussian noise. Since X is one of the channel realizations, that means it has a Gaussian distribution with zero mean and sigma variance. N is the AWGN with zero mean and sigma square variance, and P is the total receive power. When we have this structure, the resulting distribution of the output signal is Gaussian mixture. So if we look into the multiple access channel case, at this case we have k different users want to communicate with the base station. Each one has its own constellation diagram generated by different combination of these RF structures, and each user map their data to one of the channel realizations, and the received signal at the base station is summation of all the signals plus the noise, and here P again is the total transmit power. And again the distribution of the output signal is Gaussian mixture, but this time summation is over the entries of all the users in the system. So at the beginning we assumed that the entries of the constellation diagram are uncorrelated, but during our studies we have discovered that at multiple access channel case, even though the constellation entries of the constellation diagram of each user are uncorrelated from each other, the resulting covariance matrix of the some signal space has a certain structure, and it can be calculated as shown here, and rho NL here is the correlation between the entries of constellation diagram for each user. And as you can see here, even though we choose row as 0, there will be some entries with the value of 1. But this covariance matrix has a certain structure, and the eigenvalues of the covariance matrix can be summarized as follows. So M is the size of the constellation diagram, K is the total number of users, and this covariance matrix finally has M over K eigenvalues, and the largest eigenvalue has the value of K times M over K minus 1, and there are K times M minus 1 eigenvalues which have the value M over K minus 1, and all the resulting eigenvalues are 0. So when we increase the constellation size or number of the users, then the correlation effect will vanish, because number of 0 eigenvalues will increase. So if we look at achievable rates expressions for both of the systems, we can use information theoretical methods and find the mutual information between input signal and the output signal to find the achievable rate of the system. For single user case, it's the difference between entropy of output signal and the noise, and for the multiple access channel case, it's the mutual information between all the input signals and the output signal, and it's again the difference between entropy of the output signal and the noise. Here, calculating of the entropy of the noise is pretty easy since it's Gaussian. The actual challenge here is to calculate the entropy of output signal, because there is no closed form expression for entropy of a Gaussian mixture variable. So recently there was a work published by Moshkar and Kandani. They have introduced a tight lower and upper bound for the entropy of Gaussian mixture, and we can use the results from this paper to find an approximation to entropy of the output signal. So if we look into the numerical results, here for the single user link, I want to compare the correlated and uncorrelated case. With correlation and correlated and uncorrelated, I mean the entries of the constellation diagram for the single user case are there is a correlation or not. So here, blue line is the capacity, actual capacity of AWGN. Red line is when the entries of constellation diagram are uncorrelated, and green line is when there is a correlation. So we see that when we have a constellation size 4, which is pretty small, there is a gap between capacity of the channel and uncorrelated case, and also there is a gap between uncorrelated case and correlated case. But when we look into the system with 64 entries at the constellation diagram, we see that the gap between uncorrelated case and the capacity is vanished, and correlated case has almost the same performance to capacity of the channel. And here we are looking into the multiple access channel, achievable rate region of multiple access channel. Again, the blue line is capacity of the channel. Here red line is the result of the Monte Carlo simulation, which means that we have find the entropy of the output signal by using the Monte Carlo methods to calculate the integration of the exact entropy formulation. And here the green and yellow lines are lower and upper bound from the approximation. As we can see here that the approximation is pretty tight, and also the difference between the capacity of AWGN and the media-based modulation scheme is pretty small. And in this figure I wanted to look into effect of increasing the size of the constellation diagram. Here for the correlated case, we are again looking into multiple access channel. For the correlated case, we have generated the covariance matrix by exactly as shown before for the covariance matrix of multiple access channel, and starting constellation diagrams has uncorrelated entries. So we look into two different cases for m is equal to 4 and m is equal to 256. We see here that when constellation size is small, again there is a gap both between capacity of the channel and the capacity of the achievable rate of the media-based modulation for both uncorrelated and correlated case. But when we increase the number of entries at constellation diagram, the gap is closing. So if I may conclude my talk, the advantages of the media-based modulation is there is no need to increase the transmit power to expand the signal space. The only thing we need to do is adding more and more RF elements around the transmit antenna, and by doing so we will increase the size of the constellation diagram. That means that at each channel use we will transmit more information. And as shown with the numerical results, capacity of the channel is asymptotically achieved, and also the system is robust against correlation among constellation points. And this study was only focused on media-based modulation, but we can always add more bits by including also one of the conventional modulation schemes like QAM, QPSK, it doesn't matter. So the disadvantages are when we increase the size of the constellation diagram, we also increase the training time and the complexity of the system. And also at this case, linear decoding methods get even inefficient. And as I said before, we assumed that there is perfect CSI at the receiver. This is necessary because receiver needs to know every channel realization so it can differentiate between different symbols. So as a future work, we can extend our work to analyze the asymptotic behavior of media-based modulation under correlation, and we can also work for MIMO case under correlation, and we can verify the model by using realistic channel perturbation methods. Here are some of the references I have used. Thank you for watching my video.